Hello, my dear students. How are you? My name is Josia Mwakitalima. I'm a teacher teaching chemistry. So today I'm here to discuss with you some issues or problems that affect most of the students and leading them into failure of their exams. And in our subject today, we are going to consider a topic known as electrochemistry. And under this topic, we are going to consider on a subtopic known as Nernst equation. Therefore, after the end of this lesson, everyone, you will be able to determine the standard enthalpy of a cell by using Nernst equation, as well as to determine the equilibrium constant of the redox reaction. So, one is determination of EMF of a cell. Second is the determination of equilibrium constant of redox reaction. So these are the two key issues that you are going to consider in this lesson today. So let us start with the determination of EMF of a cell. But how do you determine the EMF of a cell? By using Nernst equation. Normally, Nernst equation is an equation used to determine the EMF of a cell when the electrolyte is not equal to 1 molar solution. So it's when we use the Nernst equation. But if the electrolyte contain a solution, or electrolyte contain a solution with a concentration of 1 molar solution, we employ another equation, but not the Nernst equation. So Nernst equation is specifically for the determination of EMF of a cell for a solution that contain the concentration which is not equal to 1 molar solution. So if we refer now, or we'll call from our Nernst equation, so if we call this is Nernst equation now, which is the EMF of a cell is being calculated by taking the standard electrode potential of a cell, then plus 0.0591 over n log of the reduced species over oxidized species. Now here the E is known as the standard electrode potential of a cell, and E, cell, stands for the EMF of a cell, and N represents the total number of electrons in a balanced redox equation. And the reduced species, oxidized species, are being obtained by looking on their standard electrode potential of the electrodes that are being involved in that redox reaction. So most of the students are getting a problem on to determine which species will be reduced and which species will be oxidized, so that they can use their concentration in determining the EMF of a cell. So the E of cell, the standard electrode potential of a cell, is obtained by taking the standard electrode potential of a cell at cathode minus the standard electrode potential of a cell at anode, or the standard electrode potential of a cell which is at right minus the standard electrode potential of a cell at left. So on right side is where the cathode is placed on that cell, and on left side is where the anode is placed, and on the anode is where oxidation takes place, and at cathode is where reduction takes place. So you can write this equation as E reduction minus E oxidation. Now, if you are given the electrode potential, how can you determine the species that will undergo reduction and the species that will undergo oxidation? Remember that when you are given the standard electrode potential, the species which is oxidized is the one that will have more negative standard electrode potential. That is the species which is oxidized, or the species that will have less positive standard electrode potential. And the species which becomes reduced is the species that have less negative standard electrode potential or high positive standard electrode potential. So from there now, but how? It means that if it has less positive standard electrode potential, it means that it have more negative standard electrode potential. This one have less negative standard electrode potential. That is how you can identify which species will be reduced or which species will be oxidized. But also mind you that if the species oxidized becomes to be a numerator and the species reduced becomes to be a denominator, then the sign here will change, will be minus. So next equation can also be written as EMF of a cell equals to standard electrode potential of the cell, then minus 0.0591 over N, then log of. Here now, instead of reduced species of oxidized species, will be concentration of oxidized species over concentration of reduced species. So this is the equation now will guide you to determine the EMF of a cell. Now, how to use it, then we are going to look at some simple questions that are concerned with this one. But before that one, let us go to how now can you determine the equilibrium constant of a redox reaction, because this in electrochemistry we are dealing with redox reactions. So if we are dealing with the redox reaction, that means you can have the equilibrium constant. So how do you determine now the equilibrium constant in that kind of cell? So let us consider now about the of equilibrium constant. Let us call it as K of a redox reaction. Now, if we go from the Nernst equation, this one, because oxidized species stands on the product side and the reduced species stands on the reactant side. So, the concentration of oxidized species over reduced species is equal to equilibrium constant, which is K. From equilibrium constant K, we get it by taking the concentration of oxidized species over concentration of reduced species. So from now, Nernst equation, where E, MF of a cell, is equal to standard electrode potential of a cell, then minus 0.0591 over N, then log of oxidized species over reduced species. But oxidized species divided by reduced species is an equilibrium constant, which is represented by K. So the E of a cell will be equal to standard electrode potential of a cell minus 0.0591 over N, then will be log of K, which is our equilibrium constant now. So let us make the subject the equilibrium constant, because that is the one which we are now looking for. Now, make K the subject. Making K the subject, you remember, you student, my dear students, that at equilibrium, the E of a cell is equal to 0. That is at equilibrium. So the E cell here will be equal to 0. So if we substitute by 0 there, if we substitute by 0, then that will be E0 of a cell, which is 0 now, will be equal to standard electrode potential minus 0.0591, then divided by N, then times log of K, which is the concentration. Now, if we make K the subject, then you will be having A, standard electrode potential, will be equal to 0.0591 over N log of K. Now, times N both sides, then you'll have N, standard electrode potential of a cell, will be equal to 0.059, then log of K. Now we divide by 0.059 by both sides. So if you divide both sides, then you will have 0.059, then here will be 0.0591. So log of K will be equal to N, standard electrode potential, divided by 0.0591. Now to find K, then K will be equal to log inverse of any standard electrode potential, then divided by 0.059 in bracket. So you will have now the equilibrium constant, which is K. So from there now, I'm sure once you have been given the question, you can be able to determine the equilibrium constant as well as the EMF of a cell. Now, the application of these equations, let us now, after a short break, we'll go to the equations and see how you can apply those equations in calculating the EMF of a cell as well as the equilibrium constant of a cell. Okay, welcome back for solving some sample questions that may fasten your understanding on what we have discussed. Also, sometimes you may find it in your exam. Then if you find it in your exam, I'm sure you'll be able to do it. So let us look and consider question number 1. Question number 1 is that calculate the EMF of a cell given that our cell is of lead having a concentration of 10 per negative 3 moles per decimeter cubes, with another cell which is made up of copper with a concentration of 10 per negative 2 moles per decimeter cubic, then given their standard electrode potential, which is 0.13 volts, and that of copper is negative 0.34 volts. Remember you that the standard electrode potential, to help you to judge whether it is undergoing oxidation or reduction, those standard electrode potential should be written in reduced form. So if not written in reduced form, that means you have to convert them and write them in reduced form. That's why we call them as reduction potential. So if we consider here, for example, lead here is in oxidation way, so is in oxidation form. So it means that you have to change it, and when you change it into reduction form, the standard electrode potential sign also should change. Now, copper also is in oxidized form, so it should be in reduced form. So let us now consider the data given now. The data given here is that we have the concentration of lead, which is 10 per negative 3 moles per decimeter cubic, and we have the concentration of copper, 2 ions, 2 copper, solid in reduced form, which is 10 per negative 2 moles per decimeter cubic. But you have the standard electrode potential. Remember, I have said that should be written in reduction potential. So it is lead, 2 positive in reduction potential to lead. Then the standard electrode potential now, we have been given 0.13 positive, so it will be now negative 0.13 volts. And that of copper should be also written in reduced form. Then its standard electrode potential will be equal to positive now 0.34 volts. And I said that here now you can compare, or you can know now which species have undergone oxidation or reduction. So here, lead is the species that undergoes oxidation because of the negative electrode potential, but copper undergoes reduction. So from next equation now, let us write the overall reaction equation for the 2 electrodes. Now for lead, you have seen that it is the species that undergoes oxidation. So it will be lead solid, half equations, then will be plus. Lead solid will be into lead 2 plus. This will be aqueous, then will be plus 2 electrons. So that is the half equation, the first half equation. The second half equation will be that of copper. So copper, we have said that is the species that undergoes reduction. So will be copper, 2 ions, aqueous, then plus 2 electrons, then you'll have copper solid. So do you see here now, this is equation 1 and this is equation 2. So combining the two equations, the number of electrons here too is there too. So you don't need to multiply by any variables to balance the equation. So the overall equation now will be lead solid plus copper 2 ions, then leading into formation of lead 2 ions plus copper solid. So these electrons will cancel with that one. So that is our overall reaction equation. So lead has undergone oxidation but copper reduction. Now from next equation, EMF of a cell, which is equal to standard electrode potential of a cell, then plus 0.0591 over N, then log of concentration of reduced species over concentration of oxidized species. And here reduced species is copper, oxidized species is lead. So the concentration of copper over concentration of lead. But the EMF of a cell, we said that we just get it by taking E of cathode minus E of anode. And here it will be E of copper minus E of lead, which is now E of copper minus E of standard electrode potential of lead. Then there will be plus 0.0591 over N times log of reduced species is copper. So the concentration of copper, which is 10 per negative 2 moles, or then divide by oxidized species, which is the concentration of lead, which is 10 per negative 3. So that is our equation now. But N here is 2. N is 2 from the balanced equation. So here you put 2. Now if you use your calculator, remember that here E of a cell, standard electrode potential of copper is 0.34. 0.34. Then will be minus, so it will be plus 0. Standard electrode potential of lead 13. Then will be plus 0.0591 over 2. Then times log of this one. If we divide, you'll get 10. And now the E of a cell will be equal. Now take your calculator and use your calculator to calculate the EMF of a cell. Now using our calculator, log of 10, this one is equal to 1, then it will be now 0.34 plus 0.13, then will be plus 0.0591 divided by 2, then open bracket. The answer is 0.49955 volts. So this will be the EMF of a cell that you have been asked. So have you seen now how do we use next equation in determining the EMF of a cell? And the point to consider is what I have said is to find which species is reduced and which species is oxidized. You just use their standard electrode potential that you have been given. Now let us see another example 2 of how can you use the next equation to determine the EMF of a cell. So from the second example, we have given that an electrochemical cell is constructed based on the following redox reaction. And our redox reaction, you have already given the balanced redox reaction, so it is easy. You have been simplified. So it is zinc solid plus copper 2 ions, then you get zinc 2 plus, then plus copper solid. So which means that from that equation, zinc have been oxidized and copper have been reduced. So the question continues to say that if the concentrations of copper and zinc are 0.5 moles per decimeter cubic and 0.05 moles per decimeter cubic respectively, calculate now the EMF of a cell at that temperature given their standard electrode potential as written there. So data given, we have the concentration of copper, which is 0.5 moles per decimeter cubic. And also we have the concentration of zinc, which is 0.05 moles per decimeter cubic. But also there are standard electrode potential given. We have the standard electrode potential of copper, which is equal to 0.34 volts. And we also have standard electrode potential of zinc, which is equal to negative 0.76 volts. Now, do you see here our standard electrode potential are written in reduction potential. So you don't need to change their sign. So they should appear as they are in the next equation. So from next equation, the oxidized species here, the species that will undergo oxidation now here is zinc because of the lower standard electrode potential. And the copper is the one that will undergo reduction. So the half equations of our cell now, since zinc undergoes oxidation, then it will be zinc solid to zinc 2 ions, then will be plus 2 electrons. And also copper is the one that undergoes reduction. So you will have copper plus 2 electrons, then you will have copper solid. So these are the two half equations. Then our n here is 2 because the number of electrons have been balanced by 2. So from there now, if you add and find the overall redox reaction, the overall reaction will be zinc solid plus copper 2 ions, then you get zinc 2 ions, then plus copper solid. That is our overall reaction equation. Now from there, N is equal to 2, and we know that the species that have undergone oxidation is zinc, copper has undergone reduction. So from next equation, standard electrode potential of a cell is equal to standard electrode potential minus or plus, let us use plus 0.0591 over N. Now N given there is 2, then times log of reduced species, which species have been reduced is copper, and the concentration of copper here is 0.5. So this one will be divided by the concentration of zinc, which is the oxidized species that have 0.05 moles per decimeter cubic. Now the E of a cell is equal to E cathode minus E anode, and E cathode here is copper. So it will be EMF of a cell will be equal to standard electrode potential of a cell, which is E of copper minus E of zinc. then will be plus 0.0591 over 2, then log of concentration of reduced species over oxidized species. Now E of a cell, EMF of a cell will be equal to standard electrode potential of copper, which is 0.34, then will be plus standard electrode potential of zinc, which is 0.76. It is plus because it was supposed to be minus minus. Then will be plus log plus 0.0591 over 2, then the log of 0.5 over 0.05. Now if we use now our calculator to calculate, now take your calculator, my dear student, and use it to calculate, to feed that data into your calculator and find the EMF of a cell. To compare with my answer now, use your calculator to calculate it, then so after calculating now the EMF of a cell, here is 0. The EMF of a cell is equal to 1.12955 volts. So that will be the EMF of our cell according to that question that you have been asked. So I think you see now how simple it is. So follow me to the next questions. Now the next question will be concerned with the determination of equilibrium constant, as the concept of it I have already introduced. So let us go direct to the question and see how can you use that knowledge to determine the equilibrium constant of a cell. Now from the question, the data given, we have the standard electrode potential of our cell, which is equal to 1.1 volts. And our cell equation is zinc solid plus copper 2 ions, then to form zinc 2 ions, then plus copper solid. So that is our overall equation of that redox reaction. Now let us recall ourselves from K, we said is equal to log inverse of NE over 0.0591. This is our equation for determination of equilibrium constant. Now the data given here, we have the EMF of a cell or standard electrode potential of a cell, but any value from that equation is 2. So we have all the values that can be substituted into our equation and get the answer. So K here will be equal to log inverse of N, which is 2, will be times standard electrode potential of the cell is this one, 1.1, then divide by 0.0591. So now use your calculator to calculate what will be the product and the 2 times 1.1, then divided by 0.0591, then find the log of, here you get the answer, which is 40.6091 approximately. Now find the log inverse of this answer. So you just use your calculator, then you'll have K, which is equal to 4.06. 60 times 10 power 40. So that will be the equilibrium constant of our cell that you have been asked. So that is the first equation in case of determination of equilibrium constant. So let us look another sample question that can help us to know how to determine the equilibrium constant of a cell. So there we have the question that you are given the reduction potential of the following half cells at 298 degree Kelvin, not degree. And we have the standard electrode reduction potential of nickel, which is negative 0.26, and the standard reduction potential of cobalt, which is negative 0.28 voltage. Now, using the given data to write the half equation of each electrode and identify electrode which is reduced and the one being oxidized. So the half equation, as I said, so A, half equations of the cell, you have to write the oxidation half equation and the reduction half equation. So which undergoes oxidation and which will undergo reduction. The one with the more negative is the one that undergoes oxidation, and the one with the less negative is the one that will undergo reduction. So here, cobalt is the one with the more negative. So it's the electrode that will undergo oxidation. So cobalt undergoes oxidation into cobalt 2 ions. Then it will be plus 2 electrons. So nickel is the one that undergoes reduction. So these are the two half equations showing oxidation. So this is oxidation and this is reduction. So write the half equation of each electrode. So we have written the half equation of each electrode, and also to identify electrode which is reduced and the one which is being oxidized. So this electrode is being oxidized and this electrode has been reduced. And the second part, you have been asked to write the overall redox reaction. So B, the overall redox reaction can be obtained by just taking the summation of the two equations. So take this one, equation 1 plus equation 2. So adding the two equations, you'll have cobalt solid, then plus nickel, 2 positive aqueous, then will be plus 2 electrons. No, the electrons will cancel each other because here we have 2 electrons and there we have also 2 electrons. So the answer will be now from there, the product will be cobalt 2 positive aqueous, then plus nickel solid. So this is our overall redox reaction. Species that have been oxidized and species that have been reduced. So the third part, you are asked to calculate the equilibrium constant K of the reaction. This is simple. If we go now from equilibrium constant K, which is equal to log inverse of any E standard over 0.0591. But N is equal to 2. And the E standard will be E cathode minus E anode. So the standard electrode potential is equal to E cathode minus E anode. And which one goes to cathode is now 0.28 will be 0.26 volt minus will be plus now 0.280 volts. So this is negative. So the answer will be now is 0.02 volts. So that will be the E of a cell there. Now if we substitute, the equilibrium constant K will be equal to log inverse of 2 times 0.02 divided by 0.0591. Then if you use now your calculator, my dear student, it will be so simple. Then 2 times 0.02 divided by 0.0591. Then take the log inverse of your answer. You'll get K equals to 4.75. So that will be the equilibrium constant of our cell. So now from that equation, it means that you have obtained the equilibrium constant that you were asked. This is now for the next period. So for today, let us end here, and welcome for the next lesson. And the next lesson will be dealing with how to use the standard electrode potential of cell in determination or in calculating the pH of the solution, because the pH of the solution is always calculated or is always measured by using the pH meter. So if you don't have the pH meter, how will you calculate or how will you find it? You can also use the standard electrode potential, but you also will see how can you use the standard electrode potential to predict if the given equation or the given reaction equation will take place or will not take place. So thank you for listening. Then welcome for the next lesson. Thank you very much. I'm sure you have enjoyed much. Bye.